Homework 17, read section 4.2. We're not going to go through it. There's a huge theorem in there that's central to calculus. In fact, to prove the things that we're going to do today, we would need that theorem. But as you'll see, so I kind of walk this fine line between, I'm normally very, very rigorous about everything. However, as I've said before, I think the best way to do calculus is to get in there and do it. And then if you want the rigorous treatment, then you could go back and do that stuff later. Like when you take analysis, you'll do that kind of thing. And just in the interest of time, I just want you to read it and learn the theorem. And then there's one question here, number 32, I want you to do. Clearly, there's not an answer in the back of the book. If you understand what the theorem means, you should be able to do that problem. So that's kind of the test of whether you understood what that theorem means. It's called the mean value theorem. Mean is an average. Okay, so the mean value theorem. It's central to proving so many things, and I don't want to talk about it. I'd rather just have you guys learn it because, again, we would spend a whole day just deriving it, and then that's it. But I'd rather move on and do other stuff. So, read that. Learn it, live it, love it. Do number 32. Then page 227. That's what we're working on today is section 4.3. 5, 9, 11, 13, 17. Move up 19, 25, 27, 29, 35, 37, 53, 59, and 61. And on 61, you're going to need this right here. And that's why I want to review this real quick. So, everybody got the homework? Can I erase this?
Yeah.
Okie doke. I'm erasing the homework. Now, okay, so here we go. I want a general form of a cubic. So it's the degree 3, right? It's the highest order in there. A cubic polynomial with roots at x1, x2, and x3. So how would you write this?
X minus x1 times x minus x2.
There you go, right? X minus x1 times x minus x2 times x minus x3. Is that all? Is there more to this?
Times a.
Times some number. We don't know what it is. And what theorem tells us that we could do this?
The fundamental theorem of algebra.
Good. The fundamental theorem of algebra tells us. So when I see general form of a cubic, what I immediately think is this thing right here. And this is the general form, or a general form of a cubic polynomial. And this form right here is easy to do calculus on. If I want to take the derivative of that, it's super simple. If I want to take its next derivative, that's super simple. But if you're given 3 roots, this is how you do it. So basically, the fundamental theorem of calculus tells us that you give me any polynomial like this, and we can indeed rewrite it like this, that those roots exist. And so, in other words, okay, so this is a general form of a cubic polynomial with roots at x1, x2, and x3. I'm just going to say, for your homework, like, you're going to need to know that if you're given this, there's this. Now the question is, if I need to take a derivative of this, because we're in a calculus class, like if I need to take a derivative of this, is it going to be easier to multiply this guy out?
Yeah.
Maybe. I'm going to go ahead and say on your homework, it might be easier to just repeatedly use the product rule for this. Because you can, and I did, and you guys can see what this looks like. I'm going to show the camera. That's what it looks like when you multiply it all out and you get your final. That's what it would look like in general right here. That's a lot of work to get to that guy right there.
Yeah.
And and honestly, by the time you get there, you could have just done the product rule a couple of times, because you could treat this, right? There's a constant, forget about it. So you take the product rule with this guy, and then leave, or rather, it would be the product rule of like these two and this, and you do the product rule there, and then you have another product, so you have to do the product rule, and it would get a little ugly, but I think it might be quicker. It's up to you what you want to do. You can do it any way you want. But in number 61, it says roots at x1, x2, and x3. They're not given. If, however, they were given, then life's a little bit different. And so, what I want to do, today we're going to study the geometry of a curve, right? And what I mean here is we have some curve and stuff like this, and we want to learn how do the derivatives of this curve, let's call it f, how do the derivatives determine this geometry? That's what we're going to study today. In order to do that, I want a cubic polynomial that we don't need calculus to look at and analyze. In fact, what I'm saying is, I want a cubic polynomial that I could graph. And so what I'm going to do is I want my roots to be at -1, at 0, and at 1. So let's just do that. And since I'm choosing this thing anyway, let's just pretend that a equals 1 as well. And so x minus -1 would be, I guess I could rewrite that as x plus 1, right? Now x minus 0, it's just x. X minus +1 is just +1. Now in this case, you could see actually multiplying it out is not hard because you're given actual numbers, right? There's just x minus 1. I'm going to rewrite that as x plus 1, x minus 1. First outer inner last with this guy gives me an x times x squared minus 1, which we could rewrite as x cubed minus x. So I'm going to get that back up here real quick. All right. Okay, so let's graph this guy. We know where his roots are. And right now I'm using the techniques that we developed in Algebra 2 to do this. And the way we did that was we said, okay, there's a few different things. If we know where the roots are, I know it goes through here, here, and here. So there's 1, there's -1, and there's 0. Now, here's the question. Does it go like this? Does it go like this? Which way does it go? Because remember how we did this. What? Say again?
Never mind.
Okay.
Yeah.
So the way that we did this in Algebra 2, because this is years ago now, we looked at the highest order term. And we said that determines the long-term behavior. So if you're graphing this guy, we want to know, does he go like this and like this? Does he go like this and like this? Does he go like this and like this, or like this, right? Because you have a few different options with the polynomial. But in every case, since it's, x to some power, he's going to shoot off to infinity or negative infinity. Back here, he's going to either go to infinity or negative infinity. And then what we do is we just look at the highest order term, and we say, okay, so that's going to dominate the rest of everybody else. And x cubed just looks like this right there. Then we can say, okay, so I know he's going to come up like this and down like this. And then the only question is, when he hits one of these roots, does he go through or does he bounce back? And what's the only way you could bounce back if you hit a root? So let's say we just had some regular old polynomial, x minus x1, and let's say it's squared, x minus x2, and let's say it's cubed. What you do is you say, well, when it passes over x1, the only way he could bounce back is if it's an even number, right? Because then the actual polynomial doesn't change sign. Remember that?
Right. Yeah.
That's how we derive all that. And we know that if it's odd, then when you pass through x squared, so let's say this is like a 5 and a 7, so you have your 7 here. When you're over here at 6, you have 6 minus 7 is a negative number, and then the cube keeps it negative. But then once you pass over it, right, now you have 7.5 minus 7. It's a positive number, and the cube makes it keeps it positive, and so it does that. When you have it completely broken down, like we have here, then it must change sign every time it passes through one of the roots. Yeah. So we have all this information. We know it comes from here, right? It comes from down here, and it must pass through the root. And so he's going to come up. And then he has to come down to hit this. Does he bounce back? No, because he's just a first order, or first degree, or he's a linear factor of this polynomial is probably the best way of saying it. So he comes through, and then he must come through here. So, all right, we're going to do it like this. He's going to come up, he's going to come down, and he's going to go back up. So, we have not used any calculus yet. Right? As of right now, we have only done stuff that we learned in Algebra 2. Right? And so, okay, this is what this polynomial looks like. Now let's do some calculus. I want to find this point right here and this point right here. I want to know where it occurs and what the output value is. What do I need to do?
Take the derivative and set it to 0.
It's not equal to 0. Okay, so we take the derivative, which is what?
3x squared minus 1. Yeah, 3x
Squared minus 1. And we set it equal to 0. Let's bring him over. So we have 1 equals 3x squared. 1/3 equals x squared.
So x equals plus or minus 1.
Plus or minus 1 over, how about root 3 equals x. Now, does that make sense here with what we're seeing?
Yeah.
1 over root 3 is indeed between 0 and 1. And so you have one over here and you have one over here. Okay, so we have 1 over root 3. Negative 1 over root 3. Okay, so I don't really care what the outputs are, actually, for what we're doing right now. We could do that. I don't want to waste the time. Okay, so here's the question. Without looking at f prime, let's say we don't know what f prime is, but somehow magically, maybe you were just told that this happens, okay? Without looking at that, so pretend that we don't know what f prime is. And here's the question. When x is bigger than root 3, so when we're over here, okay, is f prime of x positive or negative?
Positive.
How do you know?
Because the slope is positive.
Right. Okay, so this is what we're saying. So we're saying take any point over to the right of this point here. Okay. Now, the slope over here is positive. Therefore, whenever x is here, f prime of x is positive. Right? Okay, yeah, okay. Obviously. Now, how can you tell? The way you said it was that the slope is positive, which is absolutely correct. Another way you could look at this and see if that's the case is if the original function is increasing there. Right? That function is getting bigger. The f is increasing over here. It's also increasing over here, right? You could just look at that and see, well, it's as I run from left to right, this function's getting bigger. That means that it must have a positive slope, right? I'm kind of saying the same thing there. To say that a function has a positive slope somewhere means the same thing as the function must be getting bigger, right?
Yeah.
Okay. Okay. So here's another question. When x is between negative 1 over root 3 and 1 over root 3, is f prime positive or negative?
Negative.
It's negative. Yeah. And one way you could look at that is say, okay, pick any point in there, look at the slope of the tangent line, and the slope of the tangent line is negative, and so that must be negative. F prime, being the slope of the tangent line, must be negative. Another way you can look at it, just real quick, is say, well, it's decreasing, right? That's kind of what a negative tangent line means. It means that, well, at that point, if the slope is negative, then the function itself must be decreasing. And so, yes, indeed, on here, then f prime of x is less than 0. It is negative. Now, okay, so we just said, so let's, just by looking at the geometry of this, we were able to say, okay, in this way, f prime is, did you say positive or negative here?
Negative.
It's negative. Over here, is f prime positive or negative?
Positive.
It's positive. Over here,
Positive.
it's also positive. Okay, so it's positive. Okay. Now let's actually look at f prime. F prime of x is what again?
3x squared minus
3x squared minus 1. So let's graph him real quick. 3x squared minus 1 goes through here at 1. Is it an upwards or downward facing cup?
1. Upwards.
Upwards, because we could look at that, right? The same way we did before. And if we wanted to, we could find these zeros, which we already did, right? We set that equal to 0. We brought him over and we found one was at negative 1 over root 3. One was at positive 1 over root 3. And you could see that, so this is the slope of this. And you could see that for any interval where the derivative itself is positive, whenever the derivative is positive, then the original function is increasing. So on this interval here, so I'm just now I'm looking at the x values and I'm saying, okay, when your x value is over here, then f prime is positive. So it must be the case that f is increasing there. And I could see that, yes, it is increasing there. It doesn't tell you whether or not it's a negative number or a positive number. But what it does tell you is that from here on, that baby's going up. Same thing over here. Whenever you're over here on this interval, right, the function itself is getting bigger. Okay? Now, whenever you're down here, you look at f prime. If f prime, the derivative, is less than 0, then that means that f is decreasing here. That was terrible. Decreasing. And yeah, so I could say, okay, whenever we're between here and here, then f must be going down. And I see, yeah, indeed, he is going down through there. Everybody get that? So this is what I mean by how does a derivative change the geometry of the original curve? Or what information from a derivative, what information can we pull out about the curve? And so, like, if I were to have just drawn something like this, right? If I knew that this was f prime, or maybe it does something squirrely. I don't want that to be a nice sharp anything. I could just say, if I drew something like this, right? I could say generally, whatever point this is here, whatever point that is there, then my original f must have been getting bigger. And then at some point its slope goes to 0. Now it's getting smaller, so it's coming down. And then I guess it stops coming down at some point and its slope goes back to 0. Now its slope is positive, and so, okay. And I think you guys have done something like this before, right? You've constructed original graphs from its derivative.
Yeah.
Right?
Yeah.
Like once or twice.
Yeah.
We've done it the other way around, where we try to construct this given this, but we could do both of these. But now we want to make some definite statements. And this is, so here are some statements. How do I want to do this? How do I want to do this? Well, let's get this right here. So here's, so what I've just said is this. If f prime of x is bigger than 0 on an interval, then f is doing what?
Going up.
Which we say is increasing on that interval. If f prime of x is less than 0 on an interval, then f is decreasing on that interval. And that's all we're saying here. Okay? Okay. Now, to drive this point home, to really like get through, let's do this. Forget about this F.
Okay, we're not gonna play with the door. Fingers get caught.
Let's say that we have some function, and what we know about it is that at 0, the output's 1. Okay. So it goes through right here, 1. Now let's say the only other thing that we know about it is that whenever x is positive, so whenever x is bigger than 0, then f prime of x is bigger than 0. Now, we don't know if it's how much it's changing. All we know is that that f prime never comes back and touches the x-axis. Well, I could just say the slope here is positive, right? That's what this says. The slope is not flat and it doesn't come down. It's positive. So it must be the case that as you move this way, he comes up. Now, maybe it changes, right? Maybe it comes down. Well, it never flattens out, because if it ever flattens out, that would mean that f prime is 0.
Yeah.
So he might slow down some, but he's never gonna stop. Like, he can't ever flatten out. So it must be the case that this function, whatever it is going up.
Yeah.
Right? So I'm just saying this. I'm just going at it from the other way around, right? I'm saying, so this is, in other words, what I'm saying is that these mean the same thing. I could say f prime being positive means that f prime is increasing. Conversely, I could say, suppose that f prime is increasing, and I draw something like this. It's never coming down. It's never flattening out. It's just strictly going up. And it might go up fast and then go up slow. Then it goes up really fast and then it goes slow, but it never levels out. Well, I could say, well, on that interval where it's increasing, the slope is always positive. Right? Okay, cool. So we don't need the theorem from 4.2 because this is pretty obvious stuff. And this is what I mean. I want to get our fingers into this and pull this apart. And I think it's good to do. Again, I'm going to have you read 4.2 and you'll prove this stuff. But let's just get dirty here. Okay, so here's something, page 222. This is called the first derivative test. First derivative test. And this is on page 222. Okay, I want to get our old picture back real quick. So here was our original f, was x cubed minus x. We said he looked like this, came down and then went back up. He went here at -1, here at 0, here at +1. This was at 1/√3. This one was at -1/√3. Okay. Now, also had its derivative, which was 3x squared minus 1. And it should look like this. And it was here at 1/√3 and -1/√3. Now, check this out. This is pretty cool. Suppose C is a critical point of f. What does a critical point mean? Or a critical, no, it's, let's say critical point or critical number. Critical number, I'm sorry, critical number.
It's a maximum or a minimum or like where it blows up.
Right, but what does it mean in terms of this thing? How do you...
Wait, it's just...
If I said, here's your function, find its critical
It's
numbers.
just the zeros. The root.
-1.
Well, yeah, no, okay. You have some function. Forget about this one for a second. And I say, find the critical numbers, what would you do?
Take the derivative and set it.
Okay, so in other words, we're saying the points where the derivative is equal to 0. So I'm sorry, that's all I'm saying here.
Yeah, but
Okay,
also where it blows
so-
up, right?
Or it could be where, well, yeah, or where it blows up. Good point, good point. But here we go. suppose that c is a critical number of f. So in other words, you had some function, you took its derivative, and you found where its derivative was equal to 0. What can we do? Check this out. A. If f prime changes from positive to negative at c. Alright, so let's, before we get to the conclusion here, let's think about what that means. We're saying, so let's take this critical point. And let's pretend that we don't know what that thing is. What we could do is we're saying, okay, as we go from left to right here, what happens? Well, and I'm thinking about what my original function f must have looked like there. Okay, the original function, it had a positive slope as we're going, right?
Yeah.
So it must have done something like this. It was doing something like this. It's getting smaller and smaller and smaller and gets to 0. Okay, so it's doing something like this. It has a positive slope and now finally it gets to 0 there at the critical point. And it changes as we go through, it changes to negative. So now it's at 0 and it goes to negative. What do we call this thing?
A maximum.
Yes, yes. Then f has a local maximum at c. And indeed, that's what we're seeing here, right? It's because as we look here, it's very positive. Yep, slope is very positive. And it's getting less positive. Yep, getting less positive, getting less positive until finally it gets to 0. Now it crosses over and becomes negative. Well, what you've just done is you've traced out a bump, right? Or a downward facing cup when you see something like this, right? Okay, so B, if f prime changes from negative to positive at c, then f has what?
A local minimum.
A local min at c. And we could see that here. Here's my critical point, so I know that the derivative must be 0 there. Okay, so the derivative at that point, whatever it happens to be. And now I'm not, I know, yes, it's on this one, it's below the thing. I'm just saying we don't know what's happening here. Our slope is 0 at this point, 1 over root 3. When I go that way, it's a negative number. So as I move back, we have a negative slope like that. So he must be coming down and doing this, then he levels out. Now, as we move past it, he becomes positive. Okay, positive like that. And so that's the bottom of a cup. And so he must be a local min. And that is indeed what we see right here. As we get closer to 1 over root 3, right, he's negative, and he gets less negative, less negative, less negative, until he gets to 1 over root 3. Now the slope is 0. Now as we move beyond 1 over root 3, he starts to increase. The slope is increasing. And so he is now, right? So you're going from, another way of thinking about this is you're going from decreasing to increasing, right? Isn't that what we said about the derivative, right? That f is increasing whenever the derivative is positive. Here, f is decreasing whenever. So you're going from a function that was decreasing to a function that is increasing. And so it must be the case that your thing came down, stopped, and went back up. And so that must be the bottom of a cup, right? Meaning it's a local min, and indeed that's what we see right there. Now, there's a third statement. If f prime does not change sign, then we can conclude that there is no max or min. At C. Here's an example. So, remember remember this guy. We saw him last time. F of x is x cubed. And it has this weird thing where he's doing this thing there, and he's doing this thing there. Its slope is 0 there, but as you can see, you take the derivative, you get 3x squared. Now he comes down, the slope is 0, but he pops back up, and that's what this is happening. It doesn't, C being 0 here is a critical number, because when you plug in a 0, the derivative is 0, which means that the original function, the slope is 0, he's flat right there. But he doesn't change sign. The derivative is positive, right? So it's a positive slope. He comes down to 0, but then he becomes positive again. So that's neither a min nor a max. Okay, and we can conclude that from that. All right, questions on that? Okay, here's an example. So we're going to come back to all this later, or back to that example in a little bit. So here's number 10, and it has 3 parts. A says, find the intervals where f is increasing or decreasing, and B, find the local max and min values. So that means we're going to have to plug something in and find an output. But here we go. And the given function is, it'll be easier if I do it right here. The given function is 4x to the third plus 3x squared minus 6x plus 1. Okay, now, what do we need to do?
Take the derivative and set it to 0.
There you go. Okay, so we're going to take the derivative. What is the derivative?
12x squared plus 6x.
X squared plus
6x
6x minus 6. Now, I'm going to cut to the chase and say, you know what? I'm going to factor out a 6. That gives me a 2x squared plus x minus 1. This factors 2x and an x.
Plus 1 minus 1.
1 and a 1. And which one's which?
Minus on the left. The left, yeah.
That one's a minus? I think you're right. Yeah, because outer, inner. Outer gives me a positive 2, minus 1, positive 2, minus 1. Yes. Okay. Now, why did I do this? Well, because I want to be able to see what's happening here. I want to see. I'm going to need to graph this guy in order to find out, because first, what are my critical points?
Minus 1
1
and
1/2 and negative.
Yeah.
X equals 1/2 and x equals what?
Negative 1.
Negative 1. Okay, good. Because we're imagining now we've set this thing equal to 0 and I'm solving this, and that would give me those 2 solutions right there. And so now, okay, one last thing we need to do. Is this an upward cup or a downward cup?
Upward.
Upward cup. I know where its zeros are. One's at 1/2, one's at negative 1. It must be upward because that guy's going to dominate when x gets really, really large. And so he's going to look like a regular cup, like this. Okay, there we go. So now, let's find the intervals on which f is increasing and decreasing. So it's increasing on where?
Negative infinity to negative 1.
Yes, everywhere where this function is positive, he's going to be increasing. So from everywhere from negative infinity up to negative 1. So negative infinity up to negative 1. And that was my question, hard or soft brackets?
Soft.
It's soft because technically at 1, he's neither increasing nor decreasing. He's staying put.
Yeah.
Right? Because as we just saw, this is going to be another one of these types of things. Right? And at this point, he's not getting bigger, he's not getting smaller, he's just staying put. So technically, we gotta exclude that. Okay, is that the only place?
Union with 1/2 to infinity.
Union with 1/2 up to infinity, because we could see the derivative is positive. So really, we're just getting used to using these things interchangeably. Wherever f prime is positive, that means that f is increasing. Where is he decreasing?
-1 to 1/2 with soft.
From -1 to 1/2, because at those points he's not increasing or decreasing, he's staying put. Okay, all right, so that's the first part. That's the answer to part A. Now we want to find local max and mins. We know where they must occur, right? They have to occur at these 2 points. That's the only place where you could have that the slope is 0. So which one is the max?
Just place them.
Well, or how about we look at the geometry and you tell me. We have a positive slope going to a negative slope.
That would be the max.
Yeah, there you go. It was because as I look at this, it's a positive slope. He becomes negative, and that's what this is right here. You could memorize these two statements, or you could just remember what this means geometrically. Like that means this is the derivative of this. So that means as we approach 1, he went like this, became 0 at 1, and then came down. And so that must be the max. The max is at x equals 1/2. And then we find the max value by plugging in
-1.
f of 1/2.
Max is x equals -1, right?
Yeah, that's the one on the left. Thank you. I was like, well, half is smaller than 1, so he's the one on the left. Yeah, thank you. Thank you for catching that. The max, just like we said, just one more time, right? What's going on the graph here? Well, he's positive, he goes 0, and then he becomes negative, and so that must be a max. It's a bump, and so at -1, you plug that in, and you get, I'm not going to do it here. I think I got a 6. You could check that. I didn't do any work. I just kind of did it in my head, and I might have gotten it wrong. Where's its min?
1/2. F of x equals 1, or f of 1/2 equals.
Yeah, and again, I'm not going to just take, I want to make sure that I got this. So he's going from negative. So the slope of the thing is negative. He comes down, it becomes 0 at 1/2. Then the slope becomes positive. We go from decreasing to increasing. The thing must be a minimum. So it's a minimum at 1/2. I plug that into the original function, and I think I get -3/4. I feel a bit more confident about that because I actually wrote some stuff out. So there you go. Okay? Everybody got that? Okay. Check this out. I think, no, we already did that. We did. So we talked about with the original one that we had, right? He did this. And we saw that, yes, when you go from positive to negative, going from positive to negative, he's a top of a bump. When you go from negative to positive, that means that you were decreasing and now you're increasing, so he's the bottom of the bump. Okay? Okay. Now, check this out. I do want it back. Okay, we're going to put those back. Okay, so get rid of this stuff. Everybody following me so far? All right. Now you see what I mean by the how derivatives can inform the geometry of a function. This is what we're dealing with today. Okay. Yeah, I do want this up here. We're going to come back to this guy, our original guy, x cubed minus x. It looked like this. There's -1, there's 0, there's 1 over root 3, -1 over root 3. Another way we could look at this. So once you know the zeros, or your critical numbers, in other words, where the derivative is equal to 0, another way we could say what we just wrote up there is that if you know you have a critical number, okay, you have a critical number, we could just look at the slope here of this thing. Notice the slope is negative here. Right?
Yeah.
And that's that means the same thing as it goes from positive to negative. Because you're talking about a point that's on the x-axis, right? That's what a critical point is, right? So you take some critical number c. And what you could do is say, well, okay, we know that if it goes from negative to positive through c, then, okay, negative, positive, it must have been a min. But if that's the case, then the slope is positive through there, right? It means the same thing to say the slope of f prime
Yeah.
is positive
So that's
if it's going through here.
Right.
So look at this, slope is positive here. That means the same thing as it goes from negative to positive. Slope is negative means the same thing as he goes from positive to negative. But if the slope of f prime is negative,
so right.
that means that f double prime is what?
Positive. If the slope of
The slope of this function. So let's call this function g. You would say g prime is positive or negative here?
negative.
It's negative because
Yeah.
he's decreasing, right? The slope
Oh.
is negative there. So the slope of this function is negative. So in other words, the second derivative is negative. Does that make sense?
Yeah.
Because we had an original function,
Okay.
now we've derived a new function. So we could call it g and say, well then g prime must be negative here. Or we could remember, oh yeah, that's right, he was a derivative to begin with. So take its next derivative.
Yeah.
Okay, now same thing here. If the slope of this function is positive, then its derivative is,
Negative.
if the slope here is positive,
Positive.
then the derivative of the slope is positive, right? I mean, right?
Oh yeah.
Yeah, I mean then the,
Yeah.
the derivative of the function,
Yeah.
and so its next derivative is positive. That's what this, it means the same thing, right? That the slope of a function is negative means the same thing that its derivative is negative.
Yeah.
It just happens to be that this thing itself is a derivative. But we could say, we could just call this g of x. And then once you take its derivative, you get, well, g prime of x. We already talked about that, right? Another way of saying is like, it's increasing here, so its slope must be positive.
Yeah.
But its slope is the next derivative of your original function. I mean, I could have never said this at the first place, and we could have done all of this by just calling this function f, and we'd come to the same point that we are right here, right? And then I make the big reveal. It was a function to begin with, and then we go through and we would come to this conclusion right here, that whenever the second derivative is negative, and this guy is a critical number, then it must be the case that that's a max. Okay? Okay, we're going to come back to this in just a second, because we have to introduce a new concept here. So we'll come back, let me put this up here. So what we just said, right, and remember this is all in terms of critical numbers here. So if you have a critical number, and its second derivative here is positive, then that means, okay, you're going from negative to positive, this must be a max. Yeah? Back at the original function. We have a derivative, you have a critical number, you're going from a positive slope to a you're going from a negative to a positive, so you must have a min. Yeah. originally have them in. You have a critical number, so you know the slope is 0. You're going from a positive to a negative, which means that the slope itself is negative, which means that its second derivative is negative. At that point. Therefore, you're going from positive to negative. You must have a max. And indeed, that's what we see back there. Okay. All right. Here's a new concept. So I want to draw a function whose slope is increasing. So,
So there's so like f of x equals.
I'm going to do this way. And I'm going to do it 2 different ways here. We're going to say we start right here. And we want to say that its slope is increasing. And let's just start with a positive slope to begin with. Let's say it's like this. Okay. So as I move on, he's going to increase, but he's going to get steeper. Yeah? And he's going to increase some more and get even steeper because the slope is constantly increasing. And so what happens is this. If I were to trace out this curve, it would do this. On the other hand, I could have started with a negative slope, and that slope could increase. Something like this. You can see that if you think about the slope itself as being like a speedometer on your car or something like that, right? It doesn't matter if it's negative or if it's positive. If it's moving in this direction, it's increasing, right? It doesn't matter whether you started positive. You could start positive and increase, or you could start negative and increase. But as long as the slope of the thing is changing. Okay, so now look at this property that such a thing has. A function who, on some interval, maybe it doesn't do this forever. Maybe this is like sine and he changes as we go. But we're just talking about on this interval right here, or this interval right here. Okay? All of its tangent lines are below the curve. Right?
Yeah.
Okay, so a function with the property that all tangents are below the curve, we call that concave up. Like a cup. A cup is concave up. Okay? That's how I remember
What
it.
is the
I'm gonna get there in a second. Now remember, concave up, all tangents are below the curve. We could start with this definition, but this means the same thing as the slope is increasing.
Yeah.
The slope is increasing. So the slope is increasing. So in other words, f prime, so let's get this out of the way. Let's pick that apart here. The way I derived this is I said slope is increasing. What's the slope of f at any point?
F prime.
F prime is increasing. But f prime is a function in and of itself. And if a function is increasing, what property, the first thing we talked about, what property does its derivative have?
It's also increasing. Oh, it's the
Its
function.
derivative is, so think about this. Where is this guy increasing? Okay, he's increasing here and here. Its derivative is what there?
It's also increasing. Oh, it
It
switches from
might not be. It might not be. It could be decreasing. It just happens to be increasing. It's that it's positive.
Oh, right, yeah.
Right? Right? So wherever because f prime might be different. He could have been doing this. He could be decreasing, but it's still positive, right? So original f would be increasing here, even though f prime is decreasing. But if f prime is increasing, then f double prime is bigger than 0.
Okay.
So in other words, concave up happens exactly when f double prime of x is positive.
Yeah.
So let's kind of think back here. We said f prime positive means f increasing. Yeah?
Yeah.
F prime negative means f decreasing. Now we have some new properties. And we have f double prime positive means f concave up. And indeed, look at this. So I'm looking at this and I'm seeing it's kind of like a cup right here. That's the place where the derivative should be increasing, right? The slope is changing. And so let's take another derivative of this guy. Okay? And then we'll come back to concave down and all that, but I think right now
Concave down is convex.
it's the other thing. So here we go. So let's take the next derivative. The second derivative of this is what?
6x.
6x. Easy one to draw.
Yeah.
Okay, looks like that. F prime is positive means that F is concave up here. All of its tangent lines lie below it. But a better way of thinking about it, that means that whenever F prime is positive, that means that the slope is increasing. If your slope is increasing, you're tracing out a cup,
Yeah.
right? Now it doesn't matter where you start. Here we happen to start at a negative number, but we could have started right here where it's positive. And we're still, the slope is increasing, right? And so if the slope is increasing, then this guy is concave up. Now, on the other hand, we could say, like we did a second ago, we could say, I want to draw a function where the slope is decreasing. Okay, so I'm going to think about some function. Maybe he goes through right here, and maybe he starts off with some positive value. But if the slope decreases, he's going to increase some, but then he's going to come out. And then it's decreasing. The slope is decreasing as we go on, right? It starts up like this, and as we move, it's like, you know, your speedometer is doing this, right? It's going down. The slope is decreasing. And what we see is that such a function would lie below its tangent lines.
Yeah.
Okay? So f is below tangent lines. If a function has a property that on some interval f is below the tangent lines, we call that concave down. Concave down looks like a frown. Okay? Concave down. Okay? Now, one thing I didn't... You might think that he has to do this, but let's look at our old friend log. Log x. He's always increasing, but he's always concave down.
Yeah.
Okay? So it doesn't, this guy never needs to come back down at some point. He's just always, the tangent lines are always above this curve, no matter how far you get that way. So he would be concave down everywhere. What does concave down mean? It means that the slope is decreasing. What does slope decreasing mean? What is slope in terms of calculus? Slope is
F of 1.
Derivative.
so f prime is decreasing. If f prime is decreasing, its derivative is
Negative.
negative. So if f double prime of x is negative, then f is concave down. F double prime negative means that f prime is decreasing. If f prime, being the slope of something, is decreasing, then you're going to trace out a frown or a half frown. But there you go. F is concave down. So now, this brings us. Oh yeah, one more thing. So, this is the concave. This is the concavity test. I've just written it here, like the same way that we could say where is f increasing? We'll take its derivative and you got it. That's what it is. If its derivative is positive, then f is increasing there. Same thing here. You want to know where is f concave up? Take its second derivative and find where that's positive. Look at this. It's the second derivative of our original function is positive, and look at that. He's concave up. He looks like a cup. Second derivative is negative down here whenever x is negative. And look at that. Whenever x is less than 0, he's concave down. He looks like a frown. Okay? Everybody got it? Okay. One more thing before we put some cool stuff together. Here's a definition. Okay, I'm going to get rid of this. Here's a definition. A point on a curve y equals f of x. So you have some function, you're drawing the curve, is an inflection point. Inflection
Oh, is that where it switches?
point. If it's, first off, if it's continuous. Yeah, okay. If it's continuous, because all bets are off if it's not. Everything we've just been talking about is not necessarily true. And its concavity changes.
Yeah. So that's like at 0.
There you go. And so, where does this concavity change? Well, concavity is whether or not the second derivative is positive or negative. The second derivative goes from being negative and then changes as we go through. So again, it's not as simple as it's just 0 there. Because if the second derivative touched and bounced back, kind of like how we had with the second derivative, I'm sorry, with the first derivative. If the first derivative touches, it might not be a max or a min.
Oh yeah.
Same thing here, although we were able to state definitely that if the derivative does not change sign, then it's not a max or a min. In this case, all bets are off. You don't know anything. If it touches and bounces back, yikes! Like we can't make any definite statements. Don't worry about that too much. But an inflection point is when the concavity changes. That happens when he goes through right there. Take the second derivative and set him equal to 0 to find your inflection points. And so an inflection point, you can see, we went from being concave down looking like a frown to concave up looking like a cup at this point. This would be the point, that special point would be where the tangent line is the same thing as the slope right there. Yeah. And so, but anyway, we don't need to think about that. So when the concavity
It
changes,
starts getting less negative or...
yeah, and so you think about an inflection point. You hear this a lot, like just in regular parlance, right? Like we really hit an inflection point today in the disaster that's happening, and it doesn't mean that the trend is changing. So you think, okay, let's think about how many deaths there are in some. Of course, it has to be morbid. I can't say something nice. Like, think about how many puppies are being sold to loving families. No, it's like deaths. How many deaths are occurring in this war? And it's like, okay, and we see that, like, okay, it's increasing. It's still increasing, but it's not increasing as much as it had been, right? And so this would be your inflection point. The point where, yes, the slope is increasing. The slope is increasing. the slope is increasing. Oh, the slope is still positive, but he's no longer increasing.
Yeah.
Now the slope is decreasing. The slope's still positive, but he is decreasing. Okay, you see what's going on here?
Yeah.
Kind of the same thing here. The slope is down here. The slope is still negative, right? Meaning that. Okay, here we go. The slope is positive, but decreasing. Slope is positive, but decreasing. Still decreasing, still decreasing. It's the same trend in what's going on. He's still decreasing, still decreasing. As we go here, the slope is still decreasing. Now he's negative, and the actual function is starting to decrease. But the slope is still decreasing until we get to here. Now that's your inflection point. You're still heading towards perdition, but it's changing now. That we may be going down, right? We may still be in the valley. The function itself may still be decreasing, but things are looking up, right? We've hit an inflection point. Now the slope is increasing, and so he's increasing, and that's what concave up is, right? And so on and so forth. Everybody got that? That brings us to the second derivative test. So we had the first derivative test, and it's a test for what? Well, it's a test to find maxima and minima. The second derivative test, and this is on page 225, says, suppose that f double prime of x is continuous near C. C is a, what do we call these? Critical number. A critical number, okay? A. If f prime of x is equal to 0, well, of course, sorry, if f prime of C is equal to 0. Well, I guess C, that takes care of that. That makes him a critical number. So we didn't have to put that he's a critical number. It's just it's continuous near this number, whatever number it is. You plug it into your first derivative and find that he's equal to 0. Okay. And f double prime of C is positive, then f has a local what?
Maximum. Right.
Let's see. Hold on. So f, and this is how I have to do it sometimes, because I don't remember this statement. What I remember is this. Okay, that means the slope is increasing. If the slope is increasing, you're tracing out your concave up. So you're concave up, you look like a cup, so this must be a local what? Min. At C. Okay? And that's how I do it. I just remember that the second derivative positive is concave up. That's the only thing I have memorized. Now, if f prime of C equals 0, so the slope is 0, and the second derivative at that point is negative, concave down looks like a frown.
So
Minimum.
No, it's max.
No, I mean max.
Yeah, has a local max at C. Okay, so the slope is decreasing. The slope is decreasing. Concave down looks like a frown. You must be at the top of a hump. It must be a max.
Yeah.
Now, careful. This test is inconclusive if f double prime at C is equal to 0. All bets are off. You cannot tell one way or another. So for instance,
Oh, because it's not going to be 4 points.
when we had f of x was equal to x cubed, f prime of x was equal to 3x squared, the second derivative is equal to 6x. And at 0, the second derivative is 0. Is he concave up or is it a min or a max? I don't know. It's neither here.
Yeah.
But it could be the case, I didn't think of an example, it could be the case where it's equal to 0, but it is a min or a max. This is what inconclusive means, all bets are off.
Yeah.
With this test, you can't conclude that he's neither a min or a max. It could be possible that your second derivative is 0, but this guy is a min or a max. So you gotta be careful with that. So one last final thing I wanna do. This makes these problems much easier. So let's go back to the number 10. Okay, so I'm gonna get rid of all this. I'm gonna try to do this as fast as I can. So with the first derivative test, when we did number 10, we had f of x was equal to 4x cubed plus 3x squared minus 6x plus 1. We took its derivative and got 12x squared plus 6x minus 6. Now, if my only goal were to just tell me you find the min and the max, as of right now, we'd have to graph this and figure everything out. What's a lot easier? Well, yeah, but then we'd have to know, well, what's happening with the derivative? Is he going from positive to negative or negative to positive?
Yeah.
Right? Or we'd have to, like we did with our very first one, we were able to actually graph the function itself and then say, well, the one on the right must be that one. The one on the left must be that one. But now imagine that this thing is 4x to the 9th plus 3x to the 7th minus 6x squared plus 5. Like, I'm not graphing the derivative of that.
Yeah.
That ain't gonna happen. So if all I want to do is find the derivatives and or just find which one's a min and which one's a max, I could say, okay, f double prime of x. What's the second derivative? 24x plus 6. And I could say, okay, I found the critical numbers. This one gave us x equals -1 and x equals 1/2. And I could just say, okay, well, are we concave up or concave down at this place? And just plug it in and say, okay, f double prime, and this is what the second derivative test is. It told us how to do it. You say 24 times -1 plus 6, and I'm not even going to bother calculating it. Is that a positive number or a negative number?
Negative.
Negative. So that means he's concave.
Down.
Concave down. Looks like a frown. So then is this a min or a max?
A max.
Max at x equals -1. Okay, f double prime of 1/2 equals 24 times 1/2 plus 6. Is that a positive or a negative number?
Positive.
So
Min.
the second derivative is positive, concave up, looks like a cup, so it's a min at x equals 1/2. And you can see, like, in this case, it wasn't hard to graph this guy and actually figure it out. But, like I said, if this was x to the 7th and blah, 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 then you have x to the 6th. You're not graphing that anytime soon. And so you could just use the second derivative test, which is really nice, right? Now, the last thing, I told you on part 10, it had a part C. And all that was, it just asked you to find intervals of concavity.
So when it's concave up and when it's concave.
Mm-hmm. And that comes down to the second derivative. And we could just graph that second derivative. He looks like this. He goes through at 6. He has a positive slope, so we must do something like this. Where is that? Because that's where the concavity changes. So we need to find that place.
0.
We took a derivative and we set it equal to 0. X equals minus a 6 by 4.
Oh.
Or did I do that wrong? So minus 6 over 24. Is it a quarter?
It is a quarter. Yeah. Wait, I don't. Yeah, it's a quarter.
Well, I don't care. So whatever it is, that's the number of it. And so now we could say it's concave up on what interval?
From negative infinity. Or no, from negative 1/4 to positive infinity.
Yeah, whenever it's positive. When the second derivative is positive,
Yeah.
then we're concave up. And so, from negative 1/4 to infinity. And he's concave down.
From negative infinity to negative 1/4.
There you go. There you go.